Can you all hear me and see my screen? Thank you, Chintan. Thank you, Prasoon. Let's go ahead. So, a very good morning to all of you. In today's class, we are going to continue talking about sharpening filter or high pass filters that we started in the last class. We will learn the use of Laplacian operator today. Then we are going to make Unsharp Mask, which is a very common sharpening tool in the photographic and print industry. Then we are going to talk about gradients and typically three kind of gradient masks, that is Prewitt, Roberts and Sobel. So that is all we have for today. So we have already seen this diagram in the last class. We have seen that if this is my intensity value, then the first derivative, which is here, gives you the gradient. Gradient means slope with respect to position. So you can see that here the line is horizontal. That means the slope is 0. So this is 0, 0. And then here the intensity is decreasing. So we say that an intensity gradient exists. The first derivative will give you some value over here. Right now here it gives you minus value because you are subtracting the previous from the next. So 6 subtracted from 5 will give you minus 1. 5 subtracted from the 4 will give you minus 1, etc. So minus 1, minus 1, minus 1. From here to here, if you go, then you will find that the slope is 0 once again. Why is the slope 0? Very simple, because all values are constant. So the slope will be 0. Then suddenly there is a step here. It will shoot up and then again the slope will be 0 in this. So wherever the slope line is horizontal, the slope is 0. Horizontal line means intensity constant. The slope value turn out to be, first derivative turn out to be 0. Wherever there is a gradient, there is a slope. Wherever it exists, the gradient gives you the value. Now, just one point I would like to say. The way it has been defined over here, this line gets the negative slope and this line gets the positive slope. Although you can again get the slope, right now here it has been defined in a way that this element is subtracted from this element, that is f of x plus 1 minus f of x upon 1. That is how the derivative has been calculated. Technically, if you invert the definition, that is if you subtract this element from this, you will still get the results. Just the issue is that here you will get plus and here you will get minus. But in this, still the gradient values can be extracted. Now, second derivative we have seen that it is the derivative of the first derivative. So you take the derivative of this. So you will find that at this point it survives because there is a change. Then it vanishes here because the first derivative is constant. Again at this point it will survive because there is a change, and again it will remain 0. Again at this point, at this junction 0 to 5 it will survive, and then 5 to 0 again it will survive because there are changes, and again it will be 0. So you will detect one edge over here because there is a change in the intensity, another edge over here, there another change in the intensity, third edge over here, and fourth edge over here. And whenever there is an edge, you get a spike here. This is a lower spike, so it will appear darker. This is a brighter spike, upward going, appear brighter, etc. So this is how the spikes will appear in the second derivative. So second derivative, two-dimensional. We are all familiar in our earlier experience. It is Laplacian. So image is a two-dimensional function of position. So along x-axis and along y-axis, I can disregard the third axis. And this function we already familiar with. It is called del square operator, also called as Laplacian operator. This is along x-axis. This is the partial second derivative along x-axis. This is partial second derivative along y-axis. Now you can see we have already seen these definitions. So a second derivative along x-axis would be nothing but a derivative of the first derivative. So it will be f of x plus 1 comma y plus f of x minus 1 comma y minus 2 of f x comma y. So this we have seen in the last class. So nothing new here. Just to remember that if you add the pixel values of two adjacent pixels, that is x plus 1 and x minus 1, and subtract 2 times the pixel value at center, that is x, then you get the second derivative along the x-axis. Remember, our x-axis is vertical. Similarly, if you take y plus 1 and y minus 1 values, add them up and subtract 2 times the central value, that is y, then you get the second order derivative on the y-axis. So I can combine these two to write my Laplacian. So what is my Laplacian? So my Laplacian is these two things combined. So x plus 1 y, x minus 1 y, x y plus 1, x y minus 1, minus 4 f x y. So if I operate this on a given image element, I will create my Laplacian operator. Now I can implement a Laplacian operator by using a kernel. We have seen in the last class that how to use what you call a 3x3 kernel or mask or window to implement the algorithms. So what kind of kernel would be created? And we have already seen two kernels earlier. That is, one is the averaging kernel 1 1 1 1 1 1 1 1 1, and other one was the Gaussian kernel. So two kernels we have already seen in the earlier class. Now in this class we are going to learn how to implement these new kernels. So Laplacian kernel can be defined by having a hint that what is happening at these pixel values. So you can see that the central pixel value has been suppressed -4, suppressed by -4, while its 4 neighbors, x plus 1, x minus 1, y plus 1, y minus 1. I hope you remember the 4 neighbors and 8 neighbors. So while its 4 neighbors are at +1, -1, +1, -1. So I can use these numbers to create my Laplacian. So one of the simplest way to make my Laplacian is here. So if you look at this top left window or top left kernel, then it is using that fact that center is suppressed by minus 4, and then x plus 1 here, x minus 1 is again taken, selected, then y plus 1 is selected here, and y minus 1 is selected here. So you take this value, you take this value, take this value, take this value, and take this value, multiply to the actual pixel values, and multiply central by minus 4, add all of them together, and you get one Laplacian kernel. Now this Laplacian kernel will do an edge detection along the x-axis this way and along the y-axis this way. So it is a bidirectional kernel. So if your image has strong vertical lines and strong horizontal lines, those can be detected. However, this kernel is not an isotropic kernel. That means it cannot detect the the slopes or edges which is along the 45-degree mark. So if you want to have, or if you want to make an isotropic kernel, then this is my new definition. So here you can see that I am putting 1, 1, 1, 1 at the corners also. So here the way I am deriving my derivative is, you just have to visualize that this could be my x-axis and this could be my y-axis. So this kernel is now rotated by 45 degree. But if I superimpose the rotation on the original one, then I'll get all places filled, and there is minus 4 appearing because of this cross, and minus 4 appearing because of this cross at the center. So this will become minus 4 and minus 4, that is minus 8. So you can see that this will also give you, or this will give you the not only the vertical and horizontal edges, but it will also give you the cross edges. Especially when I say it isotropic, it is not a true isotropic. A true isotropic kernel will detect in all possible directions. This is not a true isotropic. Why is it not a true isotropic? Very simple, because it does not detect say at 30 degree. I mean, the strength of this kernel detecting a slope, an edge at 30 degree or 70 degree is very weak. But at 45 degree, yes, it will very strongly detect an edge. Minus 45 degree or 135 degree, it will detect an edge very strongly. 0 degree horizontal edges, yes, vertical edges. So all these edges will be detected very strongly. So these are the two examples of Laplacian kernel. There are others as well which are more directional. So if you want a kernel at a particular direction, then you can design it. I think the book gives you some examples. So when you do your fine reading, perhaps you can check it. Then these are the alternate definitions. As I had said just now, sometimes back, that if you invert the definition of derivative, that is, if right now when we are writing the two kernels here, we are generally defining it f of x plus h minus f of x. But if I revert it, that is, if I do f of x minus f of x plus h, then all these signs will be reverted. So plus 1 will become minus 1 and minus 4 will become plus 4. When you do that, you still extract the the edges. Your impact is going to be the same. So both can be used. I will tell you that what kind of modifications are needed when you are using these and or these. They are going to give you identical results. So a Laplacian kernel gives or highlights sharp intensity transitions. So wherever there are intensity transitions, it is going to highlight. However, we have seen that if the intensity is constant, then the second derivative vanishes. So it will not emphasize or de-emphasize the regions of slowly varying intensity. Slowly varying means where the slope is very less or zero in constant intensities. It will not show up anything. So what you will get an image is having grayish edge lines. So grayish means if it is very sharp in intensity transition, it may look even white, otherwise some shade of gray depending on the strength of the edge and discontinuities. So, and your background will be mostly dark because most of the large scale structures where the intensity is constant will vanish. So showing you one example is here. This is the image of the moon which has been taken by a simple telescope. Now I have applied 0, 1, 0, 1 minus 4, 1, 0, 1, 0. So our first of the Laplacian kernels. And you can see that here what you see is the background of the moon is completely missing. You will see a very strong transition as you are in this region is a dark gray and you jump to this, then at this boundary there is a very strong transition. So you can see that this is a very bright gray, and then as you get into inside, again that transition vanishes. You will find that there is a transition from here to here. So you will find some line not so bright gray appears. So wherever there are transitions, see here, for example, this lake. So this has some sort of boundary which appears, but outside the boundary here it is white, constant intensity. Here it is black, dark, constant intensity. Both appears dark. Outside also dark and inside also dark. So this is how typically a Laplacian taken of a source image appear. So you need to, I mean, you have, this is what you have done, you have extracted the edges. Now would you, most of the time you will find that these edges are not that great, they are not of that great use. So unless you have some method to implement or strengthen them in the original image. So that's what we do now. We take the edges here. You can see f of xy is my original image. And when you say del square, then you are taking a Laplacian. So when you take the Laplacian, you get the edge image. And then you add the edge image to the original image, f of xy, with some scaling parameter. Now the scaling parameter decides how strongly you are adding the edges. So typically, whatever kernel you are choosing, -4, -8 in the middle or +4, +8 in the middle, your C can be +1 or minus, or C can be positive or negative. And of course, if you want to strengthen it, then C values can be increased or decreased. So depending upon what kind of kernel you are choosing, you can choose a suitable C value, add it to the original, and you will get G of xy. So this is what happened. This is my original image. Now I had shown you the what you call the edge image or Laplacian of this. Now if you add the Laplacian to this image with C is equal to +1, then you get this. Now if you compare the two, you will find that definitely the edges in this right side image are sharper than the left side image. Observe it carefully. You will find this lake. The central region is typically the same, more or less, but the edges which are little blurred over here, you will find that they are sharper. Look at this crater. This crater is so more sharply defined in this. So you need to do these kind of things in order to say, suppose if you have to run an algorithm, a program where you have to say do some counting. And in that case, you have to sharpen the edges so that your counting becomes errorless. Your counting software does not take false answers. So you need to do these kind of sharpening. And it is the same process again done by using the isotropic, that is 45-degree kernel as well. So this kernel, as we have discussed, it detects the horizontal and vertical edges, and also it detects the cross edges. So if you do that, you can see that as expected the sharpening is more. Let's go back to the previous image and compare. So you can see this is the previous sharpening. Here I am using only the horizontal and vertical one written at the top and the bottom centers, and not at the corners of the kernel. And it is producing me this edge. This here I am using the kernel where 1 and 1 and 1 and 1 written at the corners too, and therefore it is more sharper. So now that takes us to an Unsharp Mask. Unsharp Mask is a very common industry tool, very common photographic tool, or it has been used by people who were printing images since ages. So this is a very common tool. So let's see how does it work. So unsharp masking consists of the following steps. You blur the original image, you take your image, you blur it, then subtract the blurred image from the original. So you find the difference, use just a negative mathematical operation. When you do that, you will get some difference. You will get a difference image. The difference image is called as a mask. And then you can add the mask to the original. So if you do that, the resultant image is going to be much sharper. By controlling the weightage, you can control the addition and hence the final effect also. So let me show you how does that work. So if this is f of xy is my original image and f bar of xy is my blurred image. So if I run say a Gaussian blurring filter, we have learned in the last class, or a typical 111 all one box filter, then you can obtain the blurred image. You subtract it from the original. So that difference will give you the mask, and then you add the mask to the original using a weighting factor, I mean a scaling factor k. So if k is 1, you just add it straight away. If k is more than 1, then you increase the weightage of the mask. If k is less than 1, then you decrease the weightage of the mask. So if k is 1, it is normally referred as unsharp masking. If k is greater than 1, then it is called high boost filtering. And if k is less than 1, then it is called as, it reduces the contributions of the unsharp mask if k is less than 1. So we are going to see that effect quickly. Just that if k is negative, then it might create dark halos or dark bands around your image. So this is how it graphically shows. So suppose this is the intensity values in the original image. It has a horizontal, that is no change in the intensity. Then there is a continuous rise, and then there is another no change. So when the continuous rise happens from no change, here it forms one edge, here it forms the other edge. Now, if you blur it, then the edges will get smoothened out. So you will not get a sharp difference here, but instead you will get a curve here and a curve here. Now you subtract this the blurred image from the original. So you will all that will be remaining is this corner and this corner. So you will get an edge over here and you will get an edge. This is your mask. Now this mask can be added to this original. So when you add this mask, remember this mask is 0 everywhere else. So here it is 0. So no change in the intensity in this part. But at this point the mask is a bit negative. So it is going to suppress these values further, while it is going to enhance this corner or this value at this position further. So you will find that our original image is largely intact, but what is happening is here you are increasing the edge value. Here you are also increasing the edge value. So your edges are sharpened. Now here few things one has to take care, that if your lower value, if it is close to the 0, then the clipping will happen, because the lowest values cannot go below 0. So if, as long as the lower value is fairly above the 0 line, this edge will get sharpened. But if this is very close to 0 line, then the clipping will happen. So it will not be that sharp. Similarly, if this has to be, if the upper value is very close to, say, your highest value, in our case it is 255, then the clipping will happen at this point and those edges will not be seen or changed very sharply. So here is an example. This is original image, this is a blurred image. Then you subtract the two, and when you subtract the two, what you get is this, and then you add this to the original. So you can easily see that you are creating a kind of a boundary to the image by finding the difference. So you will find that this is sharper than this looks sharper than this. But if you, here the k value is 1, but if you increase the k value to, let's say, 4 or 5, then in that case what happens is your border are becoming very stronger then. So that's how you will find that, I mean, it may becomes obnoxious at sometimes, it may become very odd looking. So you have to be careful. K value 1, K value 4 or 5. Now that brings us to the last idea for today's lecture, and that is the gradient operator. So gradient, as we have seen, this is the first derivative. We have already discussed the second derivative. Now we will just talk about the first derivative. What was the use of first derivative? We have seen the first derivative uses the change in the intensity values to emphasize that. So wherever there is a gradient, it will show you the value. If the gradient is a small, then the values will be small. If the gradient is large, value will be large. So in a gradient image, this will look much brighter than this one. This is anyway negative, so it will be clipped to 0. Typically, we use this kind of definition, so that can give us some idea. The gradient of an image at a coordinate xy in 2 dimensions. So I can have an x gradient and I can have a y gradient at every point. So at every point I can calculate df by dx and df by dy. The definition remains same, f of x plus 1 minus f of x upon 1. Upon 1 we are not writing. So f of x plus 1 minus f of x. This is f of y plus 1 upon minus f of y. So this will give you a 2-element matrix. So at any point you can at least calculate 2 gradients, one along the horizontal, one along the vertical. You can actually calculate the cross gradients also, but right now I'm showing you only horizontal, vertical and horizontal. If you look at this, then this gives you the magnitude of the overall gradient. The magnitude of the overall gradient. So gx is the gradient along x-axis, gy is the gradient along y-axis. So the magnitude of the overall gradient is very straightforward. It is root of gx square plus gy square. So if this is my image pixel values, remember this is not a mask. If these are my pixel values, Z1, Z2, Z3, Z4, Z5, Z6, I reminding you again, this is not a mask. These are the actual pixel values of the image. Then I can calculate Gx, say maybe at center point. So remember this was our x-axis, vertical axis was the x-axis. So I can subtract f of x plus 1 minus f of x upon 1. So that means this is f of x, then this is f of x plus 1, which is z8 minus z5. So this minus this upon 1 will give me the gradient in this direction. Similarly, g of y, so f of y plus 1 minus f of y upon 1. So this minus this upon 1, that gives me the gradient in the y direction. So these are my two gradients. My net gradient can be obtained by root of gx square plus gy square. So what kind of kernel or what kind of mask can I use to implement it? That is the question. So if you think very carefully, you will see that one element is plus and one element is minus. And this is along the vertical, this is along the horizontal. So I can take these clues and create my mask. So my mask will look like this. So whenever I implement one of the two masks, it will give me gx and gy. For example, look at this. If I take minus 1, 1, and if I implement it first element here, what will happen? So it will become z4 multiplied to 1. So z4, z1, sorry, z1 multiplied to minus 1 will give you minus z1. Okay, so z4 multiplied to 1 will give you z4, z1 multiplied to minus 1 will give you minus z1. Therefore, I can always, when I complete the convolution is, remember, we have already seen, it is sum of the products. So I take product of this with this, product of this with this, and I can sum. When I take the sum, I will get z4 minus z1. So this minus this. Then this shifts to the next pair of pixels, and when implemented gives me z5 minus z2. Then next z6 minus z3. Then z7 minus z4. z8 minus z5, etc. So applying this will give you the difference between, listen to me carefully, when you apply this you get difference between this row of pixel to this row of pixel. Therefore the gradient you will obtain is a vertical gradient here. When you are applying this, for example, minus 1, 1, so put minus 1 here, put 1 here, and do your convolution, that is sum of products. Then you will get z2 minus z1, 1 multiplied to z2 minus 1 multiplied to z1. Then add them. You get z2 minus z1. Then this shifts to the next two. You get z3 minus z2. Then similarly it comes here, z5 minus z4, z6 minus z5, z8 minus z7, z9 minus z8. So you will do all those subtractions and you will keep calculating the gradient as these small little kernels run here. These are very beautiful examples of convolution, small kernels doing the convolution. These are the simplest and easiest kernels of any type and most simplest in gradient. As I had discussed, these will give you horizontal and vertical gradients. There are cross gradients also can be calculated in a very similar way. So when you talk about the cross gradients, you say subtract z5 from z9 or subtract z1 from z5. So that will give you cross gradients, or subtract. This is one way to calculate this. This direction is one way to calculate cross gradient. This direction is another way to calculate the cross gradient. So Z8 minus Z6 or Z5 minus Z3. So you can guess what kind of kernels you will need. You will need kernels if you want to create this cross gradient. Then take a kernel which is minus 1, 1 and here 0 and 0. And if you want to take this cross gradient, then you take minus 1 and 1 in these corners and make these corners 0. So if you implement, say, for this one here, then do a convolution that is sum of products, and it will give you perfect results. So 0 multiplied z5 is 0, vanishes. 0 multiplied by z9, 0, vanishes. Minus 1 multiplied to z6 will give you minus z6. 1 multiplied to z8 will give you z8. Z8 minus z6 will give you the cross gradient. These are called Robert's cross gradients, named after the person who first published. However, we have seen that earlier lectures, earlier classes, that we prefer to implement kernels, windows, or masks in 2 dimensions and also in odd numbers. We have already seen what kind of advantages, computational advantages, symmetry advantages they can give to us. So although these two earlier masks are good, we would prefer to have a 3 by 3 kernel. I'm going to discuss a pivot kernel, which is a logical extension of the previous one. So a 3 by 3 kernel can be developed. So across, if this is my image, then all I can do is, if I want 3 by 3, then I can subtract Z7 or Z1 from Z7, Z2 from Z8, Z3 from Z9. So when we say f of x plus 1 minus f of x, instead of saying that, we will say, we will increase the interval, we will say f of x plus 2 minus f of x. So if I do that, I am subtracting elements of this row from the elements of this row, and in this way I am finding out that if there is any gradient existing in this vertical. So that can be done. Now how do I implement it? Well, this is along the x-axis, that is this. How along the y-axis? So I can subtract the elements of the last one from the elements of the first one. So if I do that, I will get the difference and hence the gradient. How do I implement? How do I design my mask, kernel, or window, whatever you call it? So you will find it very simple. All these have been weighted 1, all these has been weighted 1, while the central elements are missing, so they are weighted 0. So one can design it very straight away. So you will write minus 1, minus 1, minus 1, 0, 0, 0, 1, 1, 1. This is your mask. You implement on this. So if you do implement and do a convolution, that is sum of product, then you will find that z1 multiplies to minus 1, so minus z1. Similarly, z2 will give you minus z2, z3 after multiplication will give you minus z3. All these will become 0. These will remain positive, z7, z8, z9. So these are your product terms. When you do a sum of product, SOP, then you will add up everything together. So you get your this first one, gx, implemented by using this as the kernel. How would you implement gy now? Can you think about it? So you can see that now instead of rows, we are taking columns. So you can just rotate this by 90 degree and you get this one. So 111 minus 1 minus 1 minus 1. So 111 will preserve this, minus 1 minus 1 minus 1 will preserve these but with a negative sign. Zeros will make them vanish, and if you do the sum of the product you get this. So GY can be implemented. These are called private kernels or private masks. Another 3 by 3 mask which is very commonly used is called Sobel kernel. Typically the Sobel uses a similar kernel to that of Previtt, but instead of using minus 1 in the middle, he uses minus 2 and plus 2 in the middle. Now, using this, it does some sort of smoothing. So it does sharpening of the edges, but at rest of the places, it does a little bit of smoothing. And that way it makes very easy, I mean more useful. Typically what happens is when you're carrying out the sharpening operation, you increase the noise in the image, because remember we are doing high pass filters. They all fall in that category of filters which is called high pass filter. Now all noise is high pass, high frequency components, and they are enhanced in a huge way when you do these kind of sharpening operation. So some sort of noise reduction is handy. Sobel operator does allow that noise reduction by introducing 2, minus 2 and 2 here, or this is along x-axis, this is along y-axis, and that is why it is more often used than the other three. So let's see an example of Sobel operator here. This is an example. This is my original image. This is the gradient along the x-axis, and this is the gradient along the y-axis. So look at some important parts. So for example, as I go from here to here, you will find that this vertical does not appear in this, but this vertical strongly appears in this. So all my y gradients appear. I'm running my operator horizontally and it gives me all vertical edges. Please remember that. It is very important that if you have a horizontal calculation of gradient, that is Sobel Y operator, it gives you all the vertical edges. You can see that the vertical gradients are very sharply presented, but the horizontals are not that sharply present. Here you can see that the horizontals are very sharply presented. This is the fine example. This line is very gray, but this is very bright. So this is very sharply detected, but the vertical, look at this corner, vertical corner is detected here sharply, but not detected here sharply. All window frames which are horizontal here are very bright, but all which are vertical here are very bright. Horizontals are not. So we can, as we have seen, we can calculate under root of gx square plus gy square to give you the final image. So this is nothing but the final image, final gradient image. Okay, so that brings us to an end for this lecture. Thank you.